Let's talk about the power that runs our world, the stuff coming out of every socket in your home, alternating current. Now, AC has this weird little secret. On the surface, it seems like it shouldn't be able to do any work at all. So let's dive in and figure out why.
So take a look at this. This is basically the heartbeat of the power in our homes. It's an AC waveform, and you can see it's constantly swinging from a positive peak all the way down to a negative one, and then right back up again. This endless back and forth is right there in the name, right? Alternating current.
Okay, so here's a question for you. Just looking at this perfectly symmetrical wave, what do you think its average value is? I mean, if you consider that positive part and that negative part, what's the middle ground?
Yep, the answer is 0. A big, flat 0. Why? Because for every little bit of positive voltage up top, there's an equal and opposite bit of negative voltage down below. They cancel each other out perfectly. And right there, that's the puzzle. If the average voltage is 0, how in the world can it do anything? I mean, how does 0 volts light up your room or charge your phone? It feels like it shouldn't work. This is the central paradox of AC power.
Well, here's the trick. It turns out that when we're talking about power, that simple average is kind of useless. We need a completely different way to measure AC's punch. We need to find its effective value.
The really clever way to do this is to compare it to something we understand a little better, direct current, or DC. You know, that nice, steady, constant voltage you get from a battery? The question we need to ask is, what level of DC voltage would give us the exact same amount of power, like for heating something up, as our wavy AC voltage?
And this special power equivalent value, well, it's got a kind of scary name, the root mean square value, or RMS. Now, the name actually describes the math to find it, but don't worry about that. For our purposes, just think of it this way. RMS is the DC equivalent. It's the number that tells you the real honest-to-goodness power of an AC signal. Okay, so we have this new RMS value. How does it actually relate to the wave we were just looking at? The best way to see is to compare it to the most obvious feature of that wave, its peak.
All right, first, the easy one. That tippy-top point the wave hits on each cycle, that's called the peak voltage. Think of it as its absolute maximum height, the highest it can possibly go.
But our RMS voltage, the one that tells us about the actual work being done, is always lower than that peak. You can see it here. It's this more modest, steady value that truly represents the power we can use. So let's just break this down one more time to be super clear. Peak voltage is the tip of the mountain, the absolute max. But RMS voltage, that's the workhorse. It's the effective value. And when we're talking about power, RMS is the only number that really matters. So how much lower is it? Well, it's not random. It turns out there's a really consistent, predictable relationship. As our source material points out, the effective RMS value is always right around 70% of that peak voltage. And that 70% figure isn't just a convenient guess either. It comes from a very specific mathematical relationship, which gives us an incredibly handy conversion factor we can use all the time. This one number is like a magic key. It lets us convert from that flashy peak voltage, the thing you might see on an oscilloscope, to the effective RMS voltage that you need for any real-world power calculation. And that magic number is 0.707. That's it. That's the secret sauce that connects the peak of the wave to its actual usable power. And the best part? The formulas are dead simple. If you want to find the RMS voltage, you just take the peak voltage and multiply it by 0.707. And guess what? It works exactly the same way for current. So simple. Okay, so let's recap the big points here. Number one, this simple average of an AC wave is 0, which is pretty useless for talking about power. Number two, we use the RMS value as its effective or DC equivalent power value. And number three, you can find that RMS value just by multiplying the peak by our magic number, 0.707. Which brings us to one final thought, that 120 volts that we all know comes out of a standard wall socket. Now that you understand all this, is that the peak voltage, or is it the effective workhorse RMS voltage? Which number would actually be useful for designing and powering all our devices? I'll let you think on that one.